Hey girls, welcome to Remote Learning version 4, Lockdown 4, Locky D, as I've heard it called on the radio. Either way you look at it, it's not a great situation, but we'll make the best of it as we always do. Today we've got a really cool thing to look at, and that's the differentiation of the e to the x function. So we've been looking at the e to the x graph, it looks like that, and today we're going to derive it. Now, I think I've already let the cat out of the bag on this function, but we'll go through it and hopefully there's a few surprises along the way. So over here we've got the graph of 2 to the x, that's this one here, 2 to the x. And this dotted one here is the first derivative of 2 to the x. Pretty similar. In fact, I've said here almost the same. And it would be handy then if we knew a situation where f of x equals b to the x, so this is our exponential with a base b, and the derivative was b to the x. Gee, wouldn't that be easy? It'd be so easy to derive. So here we go, just so happens we've got the graph of e to the x appearing below, and I've asked you to draw dy dx on the same Cartesian plane. I wonder what it looks like. So I've got GeoGebra here, and I'm going to graph e to the x. There it is there. And I'm going to go f dash. Okay, and what f dash will do is just print the derivative of f. Ooh, so it's red. And hopefully you note that the derivative is exactly the same. And e to the x actually fulfills this requirement here. So e to the x is also going to be the same graph. This is dy dx equals e to the x. I think I've shown you that already, so I've kind of ruined the surprise on that, but I can never hold back on that. So you might be wondering why, and I've said here, this is my get out of jail a bit, girls. I'll go to this one a bit. There are a number of proofs or examples of why this happens, but many of the good ones require an understanding of limit laws. These are beyond the scope of the course. The book, I think the textbook says that. And truth be told, I think I used to know how to do a proof of this and how to use the limit laws, and I just can't remember how to do it anymore. So if you're really keen, look it up online somewhere. I'm sure you'll find someone out there who can explain it really well. At the end of the day, in applied mathematics, we're just going to use the fact that someone else has shown us this, and GeoGebra seems to suggest it's true, so we're just going to use it. So, our first one, if f of x equals e to the kx, use the chain rule to find f dash. Okay, so we'll go y equals e to the kx, u equals, whoops, stuff that up already, y equals e to the u, where u is equal to kx. Now, we do know how to derive e to the u, so we're just going to go dy du equals e to the u. And du dx is equal to k. Alright, so remember with the chain rule, what we do is we just multiply these two things together. So we're going to say that f dash x equals k e to the, do the u sub, which is this thing here, e to the kx. So essentially what this is saying is if you've got a dilation from the y-axis here, this k value here is a dilation from the y-axis, then f dash will simply bring that k value out the front, and it's on your formula sheet. So d dx e to the ax equals, so they just show you that coming out. So that's how it works, but from now on you can pretty much just use it. Okay, so find the derivative of the following with respect to x. So this one here is a quick one, dy dx equals, yeah, it's that easy, e to the x. Alright, this one, dy dx, according to the rule, that will just come out the front. We're going to go 2e to the 2x. If you're ever worried about it, just do the chain rule on it. So you'd go y equals e to the u equals 2x, dy du equals e to the u, du dx equals 2. They multiply to give you dy dx equals 2e to the u sub 2x. there it is there. All right, so I've just used the rule first of all, but that's the kind of method using the chain rule. All right, so let's keep going. Again, I'm going to go the rule here. So this is negative a half, so that is going to simply come out the front, e to the negative x on 2. All right, this is a bit tricky, this one. See if you can think this one through. Maybe you can do the chain in your head. So that's going to be the u. U is going to be 2x. So I think this is going to be 2x e to the x squared. But not 100% sure, so if in doubt, do the chain. Y equals e to the x squared. Y equals e to the u, where u is equal to x squared. dy du equals e to the u. du dx equals 2x. Those multiply, so dy dx equals 2x e to the u sub x squared. So I was right, but there's no harm in doing that. I can probably knock it out in my head, but you guys who are just rookie players, just use the chain. Okay, this one here, let's go y equals e to the negative 2x take 1. I'm just going to define it as y, so I can use dy dx or Leibniz notation. You can call it a function. dy dx equals. So this here, I'm going to do the chain on that, or so that's going to be e to the u. U is negative 2x take 1. The derivative of that will be negative 2. So that negative 2 comes out the front. E to the negative 2x take 1. Might be an opportune time to use our calculator to just check whether I did that right. So what we want to do is go the diff, so action, what was it again, calculation and a diff, and what we want to derive is this thing here. So we're going to go shift, I think it's 4, yeah it is, negative 2x take 1. Make sure you're in standard mode. So there we go, negative 2 e to the negative 2x take 1 with a couple of shortcuts there. Well, not shortcuts, but noting that e can be found by doing shift 4. Okay, this one here, what we'll use is the negative index law on this one. So we'll go y equals e to the negative 2x. So I'm just going to grab that, shove it in the numerator, and the index becomes negative. Take away e 3x squared. Okay, so dy dx equals, that's easy, that one, negative 2 e to the negative 2x. Now this one here, it's going to be, u is going to be 3x squared. So du dx is going to be 6x. Alright, so that's going to be take away 6x e to the 3x squared. Again, if in doubt, just do the chain rule with the u sub. Okay, find the equation of the tangent to the curve that at this point, and hence state the y-intercept and gradient of the tangent at x equals 1. So let's just do this on the calculator first of all, and just to remind ourselves, because increasingly these are 1-mark questions on the exam. So shift 7 for define, shift 4 for e, 2x plus 4. Just watch that comes out of the exponent. Okay, so we'll go interactive, calculation, line, tan line. Okay, shift 8 for the f of x at x equals 1. Okay, so that's what we should get as an answer. Let's just see if we can bang it out by hand. Alright, so dy dx equals, so that's going to be 2e to the 2x sub x equals 1 into dy dx. So we're going to get dy dx equals 2e to the 2. All right. So what I'll do now is use y take y1 equals m x take x1. Now, we're going to use this point here, so that's x, that's y. Y take e squared plus 4, watch those brackets there, equals m 2e to the 2, that's m, that's the gradient at x equals 1, x take 1, that's this value here. Alrighty, so let's simplify it up. Y equals 2e to the 2x take away 2e to the 2. Then I'm just going to add all of this plus e to the 2 plus 4. I can add it with the brackets in because it's all plus, doesn't matter. Y equals 2e to the 2x. These add together to be negative e squared plus 4. So there's our y-intercept there, negative e squared plus 4, and our gradient is 2e squared, remembering that e is roughly 2.7 ... So remember, that's a value, okay? That's not an unknown gradient or a parameterized equation. This is the equation. So that's the number 2.7 squared, which is, well, a bit less than 9, doubled, 17 or something like that. In fact, let's find out what it actually is. 2 times e to the 2. So I said roughly 17. Let's see. 14. 15. Let's go 15. I rounded there conveniently. 15, 17. Alright, so there it is. So 9G is your first lot of questions involving differentiation of e to the x.